First half is going to be a talk on like operating systems and basic operating system concepts. It might be kind of the same stuff you're learning in the operating systems course here. I'm not super sure because I haven't taken it. But I'm just trying to give a wide overview of like what operating systems do. And I'll take a look at a few like drivers, a few ways to actually interact with the hardware. And then after the talk portion, I'm going to give a demo using much less. So you guys can boot an operating system yourself, mess around with it, and get it to print stuff. All right, so just what is an operating system? An operating system manages all the hardware on your computer. It's what controls, it's what runs all the drivers on your system. It also gives you a nice interface to interact with the system, so you can get some graphics. So a kernel contains the most core functionality of the operating system. So the kernel will typically directly interact with the hardware. It'll let you run multiple processes on the computer at the same time. It'll manage memory for the operating system. It'll do all the most essential tasks that are necessary to run like every other part of the operating system. All right. So there's a few major types of kernels, monolithic and microkernels. So monolithic kernels, in a monolithic kernel, large portions of the operating system live inside the kernel. So the drivers would be inside the kernel. You've got all sorts of stuff in there, as you can see in the diagram. So this is great for speed, but it means that, let's say you have a buggy audio driver. If an attacker figures out how to take control of it, because that driver is living inside the kernel, they can actually take control of the whole kernel and of your whole computer. So if you have a buggy driver, the attacker can take control of your whole system. However, monolithic kernels are much easier to implement and generally faster. So microkernels are the other major family of kernels. So microkernels are much smaller. Significantly less stuff lives inside of the kernel. So as you can see in this diagram, all the drivers are no longer inside the kernel. They're running as user processes. And they're communicating back and forth by sending a message to the kernel, and the kernel will send a message to one of the other processes. So this means that if your driver, again, gets taken over, the attacker might be able to play weird audio to your system, but they're not going to be able to take control over any other portion of the system. So microkernels are, in general, more secure than monolithic kernels. So these are kind of like the tail ends of a spectrum. Really, a lot of operating systems are somewhere in between. Linux is more on the monolithic kernel side, because all the drivers live inside the kernel. Windows is actually closer to a microkernel, along with OS X. So it's kind of the whole spectrum. Okay, but what exactly does an operating system do? Okay, so an operating system will manage the memory of your computer. It'll control how processes get to use the RAM, the physical memory of your computer, and it'll also control how memory is allocated in processes. So whenever you malloc, the operating system will take care of that and figure out where to put that memory. The operating system will start the computer up. It'll initialize all of the hardware on your system. It'll start up drivers for all of that hardware, and it'll boot your computer all the way up to a usable interface. The operating system also handles running multiple processes at the same time. It's what makes it so you can run your browser and Vim at the same time. You're not limited to just running a single process on your computer. And then the operating system also controls the hardware of the computer. Okay, so memory. So this is a physical memory. This is your RAM. It's a huge address space, starting at an address near 0 and going all the way up to 0x, FF, whatever, that really long address. So this is one big address space. So if you have, this is great for running single programs. If your operating system just wants to run a single program, you stick it into memory, you load it to like the same address every time, so it might start at like address 1000. You start that program up, it'll run, it'll do whatever it wants with memory, and everything will be fine. However, as soon as you want to run multiple programs at the same time, you start running into issues. For one, you have to know how to divide programs up between the memory. You don't want programs to use overlapping regions of memory. And you also don't want programs to be able to access each other's memory. You don't want like Vim to be able to access the memory of your password manager and like to see all your passwords. So just using physical memory isn't good enough. So the first way that people figured out how to do memory protection is through segmentation. So this divides memory up into continuous segments. So segment 1 here might be the operating system, and then segment 2 and 3 might be user programs. So programs are only allowed to access memory inside of their segment. This means that your Vim will no longer be able to access the memory of the operating system. It won't be able to read or write from that memory. So this solves the memory protection problem. However, it's not optimal. Memory actually isn't a continuous space. There's all sorts of holes all over the place in RAM. So if you want to map a little bit of memory on one side of a memory hole and a little bit on another side, you're out of luck. You can't do that with segments. So the way that people have figured out, the way that we currently do memory protection is through virtual memory. So this maps virtual memory addresses to physical memory addresses. Each virtual memory address is mapped to some sort of a physical address. So as you can see in this, this diagram, you have two different processes. They both have their own virtual address spaces. Let me get up and point to this. So you can see this virtual address maps to a physical address up here. And each process has its own independent view of memory. This also means one of the important things this provides is the ability to consistently like load programs at the same address. Every program can think it's starting at like address 1000, and everything will be fine. They won't be conflicting at all like they would in segmentation. So this also provides for the ability to share memory between processes. So as you can see, both of these processes are sharing the smiley face at the end of memory. This is incredibly useful for doing shared state between processes. This is how you like pass messages back and forth between like different threads like quickly. So this provides for a lot of useful things. It also lets you do paging, this is paging. It lets you page stuff out to a swap file on your disk. So if you've ever made a swap file or if you have a swap partition on your computer, virtual memory is the thing that makes that happen. So I will explain that more when I get to the next slide. Here's a big diagram of how virtual addresses get mapped to physical addresses. Okay, so each virtual address is 64 bits. The first 16 bits don't actually do anything. So really, you only have like 48 bits of addressable memory. Okay, so you take the address 12 bits at a time. So first you look at the first 12 bits. This is an index into this root page table. Each process has its own root page table, which is like the root node of a tree. It gives the process its own address space, independent of any other process. So you get an index into this table, then that gives you the start of another array. You take another 12 bits, use that as an index into your new array, and you follow that to the next array. You get another 12 bits, another 12-bit index. You follow that to the next array. Finally, you're at the array of page tables. So once you're here, you get this last index. This index will point you to a page table entry, and the page table entry will finally have a pointer to what physical memory it represents. So this is the long process of what happens whenever you turn a virtual address into a physical address. So this is like would be a 4 or 5 step process every time you wanted to do a memory access. However, computers are smart, and they do a lot of caching to make sure you don't have to do like 4 or 5 steps every single time. So a lot of the time, you only have to do like 1 or maybe a couple of steps to figure out where to go in memory. Okay, so memory is split up into pages. Yes, physical memory is divided up into 4 kilobyte pages. So each chunk of like virtual memory, or how do I explain this? Sorry, this is not super well rehearsed. I guess the important thing to know here is that you can only divide memory up into 4 kilobyte chunks. So this means that the minimum amount of memory you can give to a process is 4 kilobytes. If you want to share just a little bit of state, you have to use at least 4 kilobytes. So this actually allows for a lot of granularity because 4 kilobytes is a fairly small amount of memory. Some important takeaways here. This is also how that paging to your swap file will work. So once you run out of memory, your operating system will like look at what virtual memory, look at like what physical memory a process is using. It'll copy that memory out into your swap file on your disk. It'll mark that page to show that it has been paged out. Then when that process tries to access that virtual memory again, tries to use that page, the operating system will page fault. It'll copy that memory back out from the hard drive, and it'll resume execution like nothing happened.
Is there a particular reason it's 4 KB, or is it more or less just the size that's been chosen?
The small size is useful for running a lot of processes on the computer because every single process on the computer needs at least 4 kilobytes. So it's useful for running a lot of things at the same time. There are actually larger page sizes. There's 2 megabyte pages and gigabyte pages. However, if you use gigabyte pages, you could only run like 4 different processes at the same time, assuming you had like 4 gigabytes of memory. So this just lets you run more things in parallel.
But like if I'm stupid and I'm willing to implement a really bad paging system, I could set it to whatever size I want.
Yes, you can use whatever pages you want. Okay. And like 2 megabyte pages are fairly common on like big like servers that have a lot of memory. Especially because it means you have to do less page traversals. So if you use bigger pages, you don't have to traverse 4 times. You would only have to traverse 3 times for like 2 megabyte pages or 2 times for gigabyte pages. So it can potentially be more efficient to use bigger pages. So there's some different trade-offs. You can also just intermix like different sizes of pages. Like in the kernel I've been working on, sometimes I use gigabyte pages, sometimes I use 2 megabyte pages, and sometimes I'm using 4 kilobyte pages. So you can use whatever is optimal for the situation. Right. Okay, so the operating system is also in charge of booting the computer up. So starting the computer up is actually a long and fairly complicated process. So the computer starts with the BIOS. The BIOS will initialize some of the hardware on the system. It'll initialize stuff like the floppy drive. It'll initialize, I have a list here. It'll initialize the RAM. It'll initialize the graphics to like a basic usable mode. And then it'll start up the bootloader on your system. So typically the bootloader will start in real mode. So real mode is the same mode that computers from the 80s used. This mode is like emulating an IBM PC. So it's 16-bit. You can only address 65 kilobytes of RAM. It only has segmentation and there's no virtual memory. So it's not very useful. So you want to get out of real mode as fast as possible, which is primarily what the bootloader is designed to do. So the bootloader will take you out of real mode and get you into protected mode. So protected mode is the first 32-bit mode that's available. Protected mode lets you take advantage of virtual memory and to get a full 4 gigabyte address space. However, 4 gigabytes isn't a huge amount of memory, so really you want to be running in 64-bit mode. So to get into 64-bit mode, first you have to turn the processor into compatibility mode, which is the 32-bit compatibility version of 64-bit mode. So this is the mode that your processor will switch into when you're running like 32-bit applications on your computer. So it can switch back and forth between compatibility and long mode at will. And then the operating system can finally go into long mode and to take advantage of the full like 48-bit address space.
What's the barrier from like jumping straight from BIOS into long mode?
That's a good question. It always starts in real mode. You can only get into protected mode from real mode. You can't like jump extra steps. It's just how the architecture is.
Hardware thing.
Yes, because it's designed for maximum compatibility.
So if they weren't worried about like backwards compatibility, they could design computers that went straight from BIOS into, it's just not how.
Yes. Yes, I think, I'm not sure how ARM works. I suspect ARM doesn't have as much of this like compatibility stuff. I know that Intel tried to make a new architecture called Titanium back when 64-bit was just getting started that did away with all this stuff, but it wasn't successful at all and died out. So this is just what we have because of Cruft. Okay, so typically bootloaders will just take you into protected mode. Like that's what Grub will end up doing. Wait, I think I have a bootloader slide. Yes. So Grub will end up taking you from real mode to protected mode. Some other bootloaders will take you all the way into 64-bit mode, but it all depends on the bootloader. But Grub is the most common bootloader by far. It's like the standard Linux bootloader. All right, so operating systems are in charge of handling errors and exceptions from user code. So there's 32 different exceptions that user code can throw. This is stuff like arithmetic errors, like when you try and divide a number by 0. That'll actually throw an error to the operating system, and the operating system has the option of like killing the user process or sending an error message or doing whatever it wants to. This also includes stuff like page faults. So when a user process tries to access memory that doesn't exist or that it doesn't have access to, it'll cause a page fault. And then the operating system can like kill that process if it's trying to do like malicious stuff with pages, or it might just add extra memory under the process and then just start it back up again like nothing happened. There's also a double fault here. So double faults happen if another fault handler fails. So if your like page fault handler breaks for whatever reason, then a double fault will happen. And then if your double fault handler breaks, it'll cause a triple fault, which will immediately shut your computer off and reboot it. So there's no way to handle a triple fault. So if you'll notice at the bottom of this table, I'm not sure if you can read it, there's also external interrupts and software interrupts. And these can be mapped to the same interrupt numbers as exceptions. So you want to make sure, like as the programmer, to avoid doing that. So software interrupts happen by calling the interrupt assembly instruction. So when you're writing assembly, you can write like int 32. It'll go into the operating system. It'll find the interrupt handler for number 32, and it'll run that. So this is how 32-bit operating systems did system calls. You would call like, I think it was interrupt 80. Then that's like the Linux system call handler. And then that would bring you into the kernel, and Linux would do whatever it needed to and then return a result to you. There's also external interrupts here. So external interrupts are generated by other hardware devices on the computer. So these might be generated by your keyboard. Whenever you press a keyboard key, at least an old style PS2 keyboard, it'll generate an interrupt that the operating system needs to handle right away. It'll stop whatever else is happening to handle the keyboard key. This can also happen when you get input on the serial port. You can also set up interrupts to happen. Actually, I have a slide for this. You can set up interrupts to happen whenever the floppy disk is done reading bytes. So you can like tell the floppy disk to read like a few kilobytes of like data into memory, and then you can have an interrupt set up for when that's done happening. So it'll let it like happen in the background, and then you can like the operating system can do stuff whenever that's done. So generally, these are older devices as you can see from this table. You've got stuff like the floppy disk and serial ports. Also, interestingly, they're mapped by default to vectors 8 through 15. So going back to this table, so 8 is the programmable interrupt timer, which is how you which is just like a timer that'll generate interrupts every however many microseconds. That will actually cause a double fault by default. It'll look exactly like a double fault. So as the programmer, you want to map these. You want to offset them to different interrupts. You want to stick them at 32 through whatever, or you have the option of sticking them wherever you want. But this is the default behavior. So if you're trying to do threading, you've turned on the interrupt timer to generate interrupts every so often, and you start getting double faults, this might be why. All right, so operating systems are in charge of running multiple processes at the same time. So a thread represents a running user process. It represents a single, it can represent a single program on your computer. So every single program on your computer is a thread running in the operating system. So you want to be able to run multiple of these at the same time. And you want to be able to rapidly switch between them to make it look like you're running them at the same time. So to switch between these, you need to know what state represents a thread. All right, so this is what you need to know to be able to switch to a thread and to be able to save and restore threads. So you need to know the values of all of its assembly registers. It's RAX through R15. You also need to know the values of all of these segment registers, which mostly aren't used because segmentation isn't used anymore. But FS and GS can actually be used as general purpose registers. So as the operating system, you're forced to save them. You also have to save the instruction pointer for the process. So this will let you resume execution in the same exact spot, because you don't want, if you're inside a loop inside your program, you don't want it to just switch to some other location inside your program. It would be bad. You have to save the root page table for that thread, because each thread has its own virtual address space. They each have to have their own root page table. And then you also have the option of saving some other state. You can save floating point state. It's not essential if you're in the early stages of a kernel. Saving floating point state is very expensive, and you also don't need to save it unless you're actually doing floating point math. But if you want to actually run serious user programs, you have to make sure to save it. All right, so there's two different ways that operating systems can get threads to run at the same time. One is through cooperative multitasking. So this is when threads cooperate with each other to run at the same time. So whenever a thread will run for a while. Whenever it's ready to stop running, it'll say, oh, I'm going to yield. It'll tell the operating system it's yielding, and the operating system will start up another thread. So this can actually lead to more efficient multitasking, as long as every single program you're running is well behaved. However, as soon as you get a process that just infinitely loops without yielding, your computer is stuck and it's no longer useful. The other common method of multitasking is through preemptive multitasking. This is when you generate timer interrupts every however long, I think 10 microseconds, I want to say, or milliseconds maybe. But you generate an interrupt at every certain number of seconds, and then that will cause the kernel to just switch to the next thread. So then you'll just keep switching through threads. It won't matter if the program's in an infinite loop. It'll just keep switching. All right, so finally, operating systems have to interact with the hardware some. One of the simplest components to interact with is the serial port. So serial ports can transmit 8 bits at a time, a single byte. So they're very simple to work with. You can actually get away with just outputting bytes one at a time. This is a snippet of assembly code to output on the serial port. So first you have to move the serial port number into the DX register. Then you can move the data you want to output, the byte you want to output, into the AL register, and then you just output it. So working with a serial port is incredibly simple. I believe the BIOS will even set up a good guess at a baud rate for it. So just outputting data on the serial port is super easy. This is one of the easiest ways to print things from an operating system kernel, because most emulators will support just showing serial output in a terminal. You can just output stuff to the serial port and you'll see it in on your screen. So inputting data from a serial port is a little bit harder. First, you have to run a loop to figure out if there's any data to read. You have to be looking, you can't just read in from the serial port. You have to read in from the line status register, which is an offset of 5 from the serial port. So you continually read in from this port. You do the same sort of thing where you, it's kind of like the reverse of out, whereas here instead of sticking something into AL to output, you're reading into AL. So then here you check to see if the first bit is a 1. So that would mean that there's data to read on the serial port. If there's no 1, you just keep looping. Just keep looping until you finally get a 1 on this register. And then you can actually read a byte from the serial port. So it's still fairly simple to read in bytes from the serial port as compared to keyboards. All right. So another relatively simple way of working with the hardware is through VGA. So VGA, I believe, stands for a video graphics adapter. It's one of the, it represents a bunch of different standards that evolved during the earlier years of computing to show both graphics on the screen and text on the screen. So there's a bunch of different VGA modes that represent video at different resolutions with different amounts of colors. There's also text modes of VGA, which are incredibly easy to use from the purpose of operating system development. So this means that you can get all the utility of a 80s terminal. You can get that 80 by 25 screen. All right, so this is kind of what working with that the text mode VGA would look like in Rust. So there's a big buffer in memory starting at 0xB8000 that represents all the characters on the screen. This is a big 2D array. So it's size 80 times 25. There's 80 columns and then 25 rows, I believe. Yeah, I think that's right. So it is a 2D array, even though it looks like one big single-dimensional array. You can work with it this is how you would do 2D arrays in C. So to write any character to the screen, you just create a new character. It's a 16-bit value. The lowest 8 bits of it are the ASCII value of the character you want to stick on the screen. The highest 8 bits control the color. So this lets you set the background and foreground color of the that position on the screen. Important ones to remember that 0 is black and 0xF is white. We can also get great colors like green, like bright green. All right, and then you can just create these characters and just stick them into this array. All right, so now you guys have probably already gone to this link. So I will leave it at here. So the operating system that I gave you guys is at the point where you can print stuff out to the serial port. There's a print line macro. So the goal was to get you guys printing stuff out to the to text mode, to VGA text mode. And in the README for this, the repository I shared with you guys is a link to Phil Opperman's post on VGA and the Wikipedia page for it, which are some great resources to get started on implementing this. So if you want, you can like take a shot at implementing it, and I can stick around and like help you guys, or like you can ask questions. I'm not super sure how this is going to go.
Where do we start?
Okay, do you have it downloaded?
I do have it down. I've managed to boot it with QEM yet.
Oh, nice. You did like make run. All right.
Somehow it grabbed my mouse though, and I had to kill it with P-code.
Yes, QEMU is kind of weird.